If you find maths hard, you're in good company, because some of the greatest mathematicians of the past struggled with the maths that you're supposed to know. Until a few hundred years ago, maths, like reading and writing, was the preserve of the ruling classes. Priests and scribes, merchants and scholars. But now we're all expected to use it. So we're here at the Science Museum stores in London to see where some of our maths came from. Think of a number, any number. But where did they come from and what do they mean? Our number system uses just 10 digits, 1 to 9 and 0. And depending where a digit is in a number, it has a different value. So this is 2. This 2 means 2 tens. And this 2 means 2 hundreds, and so on. Our hundreds, tens and units. And if there aren't any digits in a place, we put a 0. But it wasn't always like that. In earliest times, numbers were used to count things, bushels of wheat, sheep, and they were written as simple tally marks. But it's difficult to count a lot of tally marks. So the next idea was to bundle them into groups and count the groups. Around 5,000 years ago, the ancient Egyptians used this grouping idea in their number system. They used a series of hieroglyphic pictures, and each picture was worth 10 times more than the one before it. Number 1 was a straight line, 10 straight lines made 1 heel bone, 10 heel bones made 1 coil of rope, and so on, up to the god He, who was worth 1 million. The Egyptians made any number by using the right number of symbols. So 2084 would be 2 water lilies, 8 heel bones and 4 straight lines. At the same time, the Babylonians, who lived where Iraq is now, had a different approach. They used just 2 different kinds of arrow strokes to make all their numbers. Here's a Babylonian clay tablet at the Science Museum collection with a mathematical problem about right-angled triangles. It's written on clay because paper hadn't been invented then. And these marks were pressed into wet clay using a wedge-shaped stylus and then allowed to dry. The Babylonians counted in 60s, so to write their numbers, they'd start with lots of marks for 1 until they reached 9. Then turn the stylus on its side to make a 10. Then they'd use combinations of 1s and 10s to make numbers up to 59. The Babylonians' breakthrough was what they did next. To make 60, they didn't use a new symbol like the Egyptians did, but moved along one space and used the same mark as they'd used for 1. Then on they went, using the same set of symbols all over again and again. If there was a position with no number in it, the Babylonians left a gap, which could be a bit confusing. So they eventually hit on the idea of putting a little mark in the gap to show there's nothing there, which is the first sign of something like our 0. Here's our number 2084 in Babylonian script, which they'd write as 34 60s and 44 units. These Babylonian numbers are the first sign of a number system where the same symbols can have a different value depending where in the number they are. A place value. In China in the 4th century BC, the ancient Chinese used rods arranged on a counting board. They made different combinations of rods for the numbers 1 to 9. And once they got to 10, they moved along one place and used the same combinations of rods again, turned sideways to avoid confusion, and so on, with each position worth 10 times more than the one before it. So the Chinese number system was based on 10, like ours. Here's our 2084 in Chinese numbers, with a space where we put a 0. By about 200 AD, the Chinese had developed the abacus to do calculations more quickly, with beads on wires to make the numbers. This abacus in the Science Museum has 5 single beads and 1 bead worth 5 in each row, with each row worth 10 times more than the one before it. So this is 2084. But what was happening in Europe at this time? The Roman Empire covered most parts of Europe and parts of Africa and Asia from around 30 BC to 450 AD. The Romans used 7 capital letters for their numbers, which were easy to carve into stone or scratch in a wax tablet. Paper still hadn't been invented yet. These letters went up in multiples of 5 or 10, and the Romans made all their numbers from them. So here's our 2084. This wasn't a place value system like the Chinese or Babylonians, because it used different symbols for each value, more like the ancient Egyptians. The Romans had no zero, big numbers were really awkward, and multiplication and division was very difficult. Despite all these drawbacks, Roman numbers were still used in Europe by church and state officials for centuries after the Roman Empire had collapsed. But the number system we use now is nothing like the Roman system. So where did it come from? It was in India from around the 4th century AD that written numbers started to appear that we'd recognise. They used different symbols for the numbers 1 to 9 and moved them along one place for each multiple of 10. And instead of leaving a gap where there were no numbers, the Hindu mathematicians used a little dot or a circle, the first sign of a proper zero. News of the new numbers soon spread to Europe. Early in the 13th century, the famous Italian mathematician Fibonacci wrote about them in his book of calculations. The 9 digits of the Hindus, the knowledge of the art of which very much appealed to me. And he explained how, with just these 9 figures and the sign 0, any number may be written. But despite Fibonacci's enthusiasm for the new numbers, the authorities in Europe preferred to stick with the old Roman numbers they'd been using for 1,000 years before. This held up mathematical progress in Europe for years, and it wasn't until the 16th century that the Hindu Arabic numbers we use today finally become established. In his book, Fibonacci also wrote about how to work with the new Hindu numbers. This shows how to multiply large numbers using the Hindu grid system. And this is how it works. To multiply 56 by 28, you draw up the grid and fill it out by multiplying each pair of digits in turn, like this. And then add the results in each diagonal. So our answer is 1568. By the end of the 16th century, this was a standard method of doing multiplication. In the early 17th century, the famous Scottish mathematician John Napier invented a simple calculator to help with this grid multiplication. They were called Napier's bones, and here's a set in the Science Museum's collection. You arrange the bones to make the number you want to multiply, say 2084. And to multiply by, say, 4, you'd read the results across the 4th row, adding the digits in each diagonal to get 8336. From then on, more devices were produced to help do calculations quickly, such as mathematical tables and slide rules, and mechanical calculating machines that use gears and cogs to add, subtract, multiply and divide. Multiplication is repeated addition. So to multiply 56 by 28, you turn the handle 8 times for the units, and then move the carriage along and turn it twice with the tens. By the 20th century, electronic calculators made working with numbers even easier. Now we can get an instant answer to the most complicated problem, but it will only be the right answer if we put in the right numbers and press the right buttons. But whilst modern electronic calculators make working with numbers easy, they also make it easy to forget how our number system works and how wonderful it is. If you find negative numbers difficult to understand, you're in good company. As recently as 1759, a famous British mathematician wrote that negative numbers darken the whole doctrines of the equations and make dark of the things which are, in their nature, excessively obvious and simple. And he went on to conclude that negative numbers were nonsensical. You can understand him saying that because, after all, numbers were used to count real things, and mathematics was about calculating real quantities. So how can there be a quantity that's less than nothing? It's not surprising negative numbers posed a problem. In ancient times, the Greeks had no negative numbers because their maths was based on geometry, in which numbers represented real lengths, areas or volumes. Around 250 AD, the Greek mathematician Diophantus wrote a famous book about equations and looked at what we'd write as 4x plus 20 equals 4. Now, the Greeks didn't write equations like we do, but would say something like, how many things, when multiplied by 4 and added to 20, is equal to 4? But Diophantus pointed out that 4 is smaller than 20, so that's absurd. And so it would be to the Greeks. Our solution of x equals negative 4 would be completely meaningless. In India, in the 7th century, the famous Hindu mathematician Brahmagupta explained negative quantities in terms of debts, and he came up with some rules for doing arithmetic with them. A fortune subtracted from 0 is a debt. A debt subtracted from 0 is a fortune. And a debt times a debt gives a fortune. We'd go along with that now, but mathematicians remained very suspicious of negative numbers for centuries to come. Even in 16th century Europe, resistance to negative numbers continued because most maths was still based on practical activities, such as science, commerce or warfare, in which negative numbers had no meaning. Mathematicians still called them absurd and rejected negative solutions of equations as fictitious or false roots. It wasn't until the 17th century that an English mathematician, John Wallis, came up with a novel idea of explaining negative numbers by showing where they come on a number line. In his treatise on algebra, Wallis gives the example of a man having advanced 5 yards, thence retreat 8 yards, and it be then asked how much is he now advanced, I say because positive 5 subtract positive 8 equals negative 3, that he is advanced by 3 yards less than nothing, which is exactly how we think of numbers on a number line today. And now, negative numbers are on the school syllabus, so you too can relive, but hopefully avoid, the difficulties that plagued the famous mathematicians of the past. For as long as people have engaged in trade or built things, they needed to measure things, and much early mathematics was based on calculations that used these measures and recorded the result.